Hey folks, thank you for joining. People that are just joining now, if you can mute yourself. And we have the immense pleasure to have Emily Lichko, if I said correctly your last name, from University of Arizona. It's part of our SHIELD webinar series called Young Voices. And Lichko research focus on kinetic plasma physics processes, both in space and astrophysical plasma, so it's general. And she's interested in particle heating and also nonlinear processes that affect plasmas. It's mainly collisionless, but also anisotropic plasmas. She received her bachelor in University of Michigan in applied math and physics in 2013, and her PhD from University of Wisconsin-Madison under Jan Egedal. I knew Jan when he was back here at MIT. That's fun. Dr. Lichko is currently a NSF postdoc research fellow at the University of Arizona, working with Professor Chris Klein on the effect of linear and nonlinear physics on onset and evolution of microinstabilities in space-relevant plasmas. Let me share my screen and show you guys a beautiful poster. What she's going to talk today will be effects of distribution structure on prediction of plasma behavior in marginally unstable plasma. What we usually do in those webinars, both the ones that talk about science and others that talk about their personal journey, is to have the speakers talk, and we usually reserve 10 minutes at the end for questions. So if you have something in mind already, put in the chat, and 10 minutes before we'll give a warning to Emily, and we'll try to wrap it up to have time for questions. So just a quick overview. This webinar is part of our NASA Center SHIELD, and I'm the PI, and John Richardson is the program manager. The SHIELD vision is to develop a predictive global model for the heliosphere. SHIELD stands for solar wind with hydrogen ion charge exchange and large-scale dynamics. And we use a whole sort of models, both big ones, the big global MHD, as well as the small ones like particle in cell and hybrid. And of course, all the observations that we have of the outer heliosphere, energetic neutral atoms, in situ measurements to try to reach this goal. And if you want, check our website, there's lots of activities there. And the main drive behind it is also on habitability, trying to connect what we know about prediction about our astrosphere in terms of the big pictures of astrospheres out there. Here's a website, so you can look in research, outreach, and news. In terms of outreach, we had this initiative to try to tell different stories of different trajectories that people have as scientists. Some of them touching in very universal themes like being an immigrant, being gender fluid, being the first in your generation to be a scientist, etc., etc. So go check it out. These testimonials are incredible. I get goosebumps every time I listen to them. And if you want to have a testimonial, especially if you're in a younger part of your career, we would love to hear from you. And if you have an interesting story, just reach out to us, and we can help you plan this recording. It's very informal, as you can see in these recordings. It's not high tech. We do have a survey at the end of the webinar. I'm going to put it in the chat to help us prepare for later on other webinars. So if you can just take a couple of minutes and fill it out, we will thank you. And especially because this webinar is related with young voices, we wanted to remind you that we have a happy hour that we started a couple of months ago, and it's immediately after this webinar. I'm going to put in the chat on Nick Gross that is here that the happy hour for us can put that in the chat the link to register. Sorry. So you can come immediately, you are welcome. And just to advertise, the next webinar will be by Mayra Monteros and Laura Delgado. They're both in NASA, and they're going to talk about what is to come from a Latin immigrant and from Latin experience into being a scientist and a manager. So the title that they gave is From Puerto Rico to Outer Space, de Puerto Rico al Espacio Sideral. And with my portuñol, I can understand a little bit of this title. Okay, folks, I'm going to stop sharing and give to Emily to share her screen. Hi, Hans.
All right. Okay, so thank you for having me here today. I'm Emily Lichko, I'm a postdoc at University of Arizona. And so today I'm going to be talking to you about the effects of distribution function structure on predictions of plasma behavior in a marginally stable plasma. So before I begin, Merav told me as I was putting together the talk that I should put together a couple slides on how I came to be in the field. So I did my undergraduate at the University of Michigan, and I did research in a couple of different areas, where my undergraduate thesis work was in quantum computing. And so I went into graduate school at the University of Wisconsin with every intention of continuing on in quantum computing and getting a PhD in the subject. But once I got there and I started doing research, I pretty quickly realized that it just wasn't the best fit for me as a field or as a research subject. So I started looking around at the other areas of research at UW-Madison, and along with quantum computing, the university has a really strong program in plasma physics. And so as I started looking into the field, there were a lot of aspects that really appealed to me. Number one is that I thought just the physical systems themselves were incredibly interesting and dynamic. There are these incredibly energetic cosmic rays that shoot in from outside the solar system. The sun's hurling pieces of plasma the size of Mount Everest into space. And even on these smallest scales, the space isn't filled with this pristine, calm, cold vacuum, but this roiling, chaotic plasma. So I really liked that aspect of it. I also like that I got to use a combination of theory and computation and observation. So I just wasn't doing the same thing all the time. And one thing that I would say I didn't really appreciate at the time, but I've really grown to appreciate as I spent more time in the field, is how you get to really work on fundamental physics questions. So I've used things from all of my core physics classes. So quite a bit of E&M, but also mathematical techniques from quantum, and just a surprising amount of stat mech in the work that I've done. And so I would say I've been really lucky to have really great mentors, both my research advisor, Jan Eggedal at the University of Wisconsin, and then also Chris Klein at the University of Arizona. And I'm really excited to talk to you today about some work Chris and I have been doing about capturing the details, how capturing the details of the distribution function can lead to better estimates of the dynamics of the plasma. So I know that this is kind of a mixed group in terms of knowledge of, let's say, kinetic plasma physics, and there's some undergraduates and graduates. And so I'm going to try to go into a little bit more background than I would ordinarily. So we know that because of the incredibly low collisionality in space and astrophysical plasmas, distributions of ions and electrons we observe are not Maxwellian and are in fact far from thermodynamic equilibrium. So the non-Maxwellian features in these distribution functions, such as temperature anisotropies or beams of electrons and ions, are source potential energy and can act to destabilize the plasma. So these off-Maxwellian velocities can add energy to the electromagnetic fluctuations or subtract energy. And the destabilization of the plasma due to these off-Maxwellian features is called a microinstability. So these instabilities are important as they likely play a role in some of the largest open questions in solar physics. So we have the coronal heating problem, where the temperature of the solar wind jumps from about 6,000 degrees Kelvin on the surface. Oh, sorry. About 6,000 degrees Kelvin on the surface of the sun to over 1,000,000 degrees Kelvin over the course of a few tens to hundreds of kilometers, far faster than can be accounted for by diffusion alone. So even past that point, there's the heating of a bulk solar wind, and then also the presence of high frequency waves that are observed outside of the range that are predicted by the Alfvén cascade. These are just a few of the problems that these kind of waves and instabilities play an important role in understanding. So differentiating between the different explanations for these observations requires a good understanding both of the timescales that the instabilities are generated on, as well as the characteristics of the associated wave. So with kind of this complex dynamic computing process, it's very difficult to tell what's going on. So traditionally, to tell which waves are present and what the plasma is doing, one of the tools that people have relied on are linear theory. So there's a tremendous amount of information in the structure of these distribution functions, but they're typically only represented as a fit of two Maxwellian or bi-Maxwellian distributions. So one of the central questions of the talk is how much information in the distribution function is needed to accurately predict the behavior of the plasma. So I'm going to start off by talking about how well the fidelity of the representation of distribution function affects our predictions for the stability of the plasma. And then later on, I'm going to go into the second question where when does this linear description just completely break down? So I've been looking at these questions using a 1D electrostatic simulation of the two-stream instability. So here we have the distribution function of electrons as a function of velocity. And so this, because we have two electron populations with this drift speed, that's going to give us the potential energy that we need to drive these instabilities in kind of this marginally stable situation. So the plasma in the solar wind is marginally unstable. It's a subject to a variety of competing processes that push it both towards and away from the boundaries of various instabilities. This case study of the two-stream instability that I'm going to be talking about today is likewise in the same kind of marginally unstable regime. So while it's unstable, it's not so violently unstable. The original mode I set up is going to dominate the entire simulation and suppress all other modes. I mentioned this point because it turns out that as the plasma evolves, there are interesting dynamics that will evolve as a function of space and time that aren't necessarily present in more extreme cases of the two-stream instability. So just go through the parameters. We ran this using VP, which is a 1D, 1B electrostatic solver, originally published in House et al., mass ratio of 100, small initial perturbation, kind of set up the additional mode, and then we've got this drift speed, and that's going to drive our perturbation, or drive our instability. So in this case study of the two-stream instability, we're going to look at to what extent the fidelity with which we represent the distribution function affects our ability to describe the behavior of the plasma. So the distribution function itself has all the detail as I run it in the simulation itself, but when I analyze it and try to get out what waves are present, I'm going to represent it as a sum of Maxwellians. So instead of thinking of the distribution as a sum of two Maxwellian fits, I'm going to represent the distribution function using a basis of Maxwellians. So for this 1D, 1B case, each Maxwellian contains three parameters that contain information about the plasma. So we've got the density, we've got the temperature, and then we've got the drift speed. So as long as the number of velocity points is greater than 3 times the number of Maxwellians used to represent the distribution, there's no danger of overfitting the distribution function. So as I'm doing a simulation, I have the luxury of using 512 points in velocity space. But even for a spacecraft that has 16 or 32 points of velocity space, the distribution could still be represented with 5 or 10 Maxwellians, and we could get more and more. We get much more information out of the distribution function than we would have with, say, 2. So quick note, so I am doing 1D, 1V simulations, but there is that spatial variation along that one spatial dimension. But the distributions I'm going to be showing you here today are all box average. So while they have more information in velocity structure, I'm still wiping out some of the information in spatial structure. So I'm going to come back to that point later on in the presentation. I just wanted to point out that this is the box average, not the actual a single point in space and time distribution. So before I get into the actual results, because again, this is a mixed group, I wanted to talk a little bit about how we get these predictions of the growth rate of the plasma. So we start with the Vlasov and Poisson equations, so information about the distribution function in the Vlasov equation, information about the field in the Poisson equation, because again, this is electrostatic and we don't have those magnetic fields. And then we assume that the distribution function can be expanded in terms of some small parameter epsilon. So we have this distribution function with all the structure, and we only keep the first order structure. such that it is uniform in space. So we do some math, but essentially what we do is we combine the information in the Blasov and Maxwellian equations, and we get an expression for the dispersion relation, which is what waves are going to be present in the plasma and how is energy going to be transferred in between the waves and the distribution function. So using that basic method, we put in our 220 fit distribution functions into our dispersion relation, and we get these growth rates. So here I have, again, the boxed average distribution functions. And then over here on the right, I have this plot of the energy in the fields as a function of time. So the black line is the actual energy in the fields. The green line is the predicted energy in the fields using the growth rate from only 2 Maxwellians. The purple is the predicted growth rate using 4 Maxwellian representation. The pink is a 10 Maxwellian representation, and the orange is a 20 Maxwellian representation. So we can see that even though the 20 Maxwellian representation and the 2 Maxwellian representation both look fairly similar, and if we look at the least squared fit, we can see that they're both doing a great job of representing the distribution of, they both have very high fidelity of what the actual distribution function is doing. Those small variations in the distribution function can make a huge difference in our prediction for what's happening in the plasma. And we get a much better fit with the 20 Maxwellian representation than we do with the 2 Maxwellian representation. So just to dig down into this plot a little bit deeper, so you'll notice that I have this strong, this bold central line surrounded by kind of this, this lighter shaded region, the same color. So what is actually happening is this central line is the average value of the growth rate, and the shaded region is the space mapped out by 4 different representations, 4 different initial conditions of the growth rate, initial conditions of fits to the of Maxwellian representations of the distribution function, so that leads to some slight variation in fits. So the reason I chose, I have up to 20 here is because if you look, say, over a particular region in time of how the growth rate, both the average and the spread, changes as a function of the number of fits that you use to represent, you can see that there is a point at which the average growth rate stops changing and we get this asymptotic behavior. And so the reason I'm using 20 is because based on this particular setup, it looks like 20 is about the place where we have a converged fit and we're getting all the linear information that we can outside of from the distribution function. All right, so why does the 2 Maxwellian, why is there such a big difference between a 2 Maxwellian and a 20 Maxwellian representation of these distribution functions? So up here I have the 20 Maxwellian fit. So the black line is the actual distribution function. The orange dashed line is the 20 Maxwellian representation. And these blue lines down here are the actual 20 Maxwellians that I sum together to represent the distribution function. And then I've got the same down here for the 2 Maxwellian representation. The black line is the actual. The 2 blue lines are the 2 Maxwellians summed together to get the distribution function. And the in both the 20 and the 2 Maxwellian representation, the pink and the blue lines are the locations of the 2 fastest growing modes in velocity space. So the actual mode itself is related not to the distribution function, but to the gradient of the distribution function. So if we look at this next plot and the gradient of the distribution function in velocity space, we can see that at these resonant velocities, we have a much higher fidelity. Sorry. We have a much higher fidelity. We have a much better agreement between the 20 Maxwellian representation and the actual distribution function than we do in the 2 Maxwellian representation and the actual distribution function. So we can also use the compare 2 different 20 Maxwellian representations and see why we get this kind of variation, these broad bands around the average. So if again, we look at the gradient of these distribution functions and specifically the density times the gradient, we can see that even though they have very similar shapes and, similar values at the resonant velocities, there are some small variations due to the adding up of 20 Maxwellians that are going to give us slightly different velocities and give us that spread in the distribution function. All right, so this is how does the fidelity of our representation of the distribution function affect our predictions for the stability of the plasma. And so now I'm going to get into when does the linear description of the plasma break down? When does this linear framework that I've been using to actually describe what's going on, like when can I not use it anymore? And so for that, I'm going to have to go back to the equations again. So I told you early on that in the traditional derivation of these linear waves, we take the Poisson equation, we take the Vlasov equation, we combine the information in the distributions and in the fields. We assume that the actual distribution function, we get rid of some of the structure in the distribution function to make the calculation easier. And we combine the information to get the dispersion relation and to get what waves are going to be present in the plasma and how that energy is going to be transferred between the distribution function and the waves. So instead of doing that traditional form, we can do kind of a more general formulation. So we still start with the Vlasov and Poisson equations, but this time, instead of making assumptions about the distribution function, we just combine the two equations. And so we can look at the actual equation itself without making any assumptions in the distribution function and get a lot of insight into what's actually going on when we make this assumption of the distribution function. So if I were to say, make the same distribution function expansion that we did before, you would still get the same dispersion relation that I used in the previous plot. You would get the exact same results. But if we were to split the distribution function into an FL and an FNL, a linear part and a nonlinear part, where the linear part contains all the linear information in the plasma. And so that's going to be all the information in the plasma that doesn't depend on the spatial variation. Because what's actually happening is that the part that we can't take out of this integral is this gradient in space. And so when the distribution function is constant in space, when we take that box average, but we don't throw away additional information like we do in the kind of traditional approach, we can get a lot more information about the distribution function. And so that's when the 20 Maxwellian representation is going to fit better than the 2 Maxwellian representation, because we're keeping in more information about that linear distribution function. And so we're getting a better representation of the plasma. And so there are one of the points at which this description is going to break down is when we can't ignore the effects of spatial variation. So when the spatial variation in the distribution function is going to have such a large contribution that the linear description is no longer a good description of the plasma. And so that's kind of what we're seeing at the end of this plot. So the 20 Maxwellian fit is a very good representation up to about, I would say, 25, 30 omega PE. And then in case we can see it's kind of starting to pull away, these 3D effects, these nonlinear effects are starting to come into play and the linear description is breaking down. So in addition to that point, something that I've glossed over is that this dispersion relation doesn't just predict a single mode. So here I have an example dispersion relation. I know this is a plot that many of you are probably not used to reading. So here we have, so the dispersion relation is what modes are going to be present in the plasma. So the white dots are the poles that represent the modes that are going to be present. And then we have it here as a function of gamma and omega, where gamma is the growth rate, omega is just the frequency of the wave. And so we can see that there's this large growth rate, and then the second fastest mode significantly smaller. So usually what you think of is that fastest mode is just taking off and completely damping all the other structure that's in the distribution function. And so But what I'm going to be looking at in the rest of the presentation is, are we properly accounting for the energy and the modes predicted from our linear description of the plasma? So in order to look into this question, I ran some additional studies of this marginally unstable two-stream instability. So I ran 5 different cases. The red is the initial case that we were looking at before. The green, light blue, dark blue, and black are with progressively smaller and smaller relative drift speeds. So over here, I crossed the margin of stability. So round about drift speed of 1, the plasma is no longer unstable. And so while technically there is a drift speed, it's not enough deviation from a Maxwellian. It doesn't have the potential energy resonance to really drive that strong instability according to kind of linear to Maxwellian theory. And so we can, for each of these runs, we can look at the J dot E, which is going to be the energy transfer between the waves and the particles, as a function of initial drift velocity, and see how much energy is transferred between these waves and particles. So it's a little difficult to see because there is this oscillation as a function of time. So I average over the period of that oscillation you saw before and get these trends that you see here. So the averaging creates these artifacts at the beginning and the end. Those are not physical, those are just a function of the averaging. But you can see that even for the drift velocities that should be below this margin of stability, we still do end up getting this slightly positive slope and getting some positive growth, even for the 1, and then more dramatically for the 1.35 and the 1.75. So in order to look at, compare this to the energy in the fastest growing mode, I want to take a second and talk about how we calculate the energy in a given mode. So here we have the expression for the collisionless power absorption from sticks. Omega R is the real part of the frequency. E is the electric field, and then EA is the value of the dispersion relation at the time where there's 0 growth. So for a given electric field, we get this expression. And so with the electric field of a given mode, usually the fastest growing mode is this expression. So omega R E naught is given by the actual magnitude of the electric field. And so essentially the dependence is going to be on that E to the 2 gamma T. That's going to be how the power changes from this fastest growing mode. So we can compare how these fastest growing modes for these middle 3 distributions affect the behavior of the plasma. So for the dark blue, that again should be below stability. Light blue is kind of the margin of stability, and green is should still be unstable. So in the black line, we've got the J dot E averaged over time. The red line is the energy from the growth rate predicted by the 2 Maxwellian fit. The blue is the prediction of the growth rate from the 20 Maxwellian fit. So because I have multiplied just by a constant and not by its actual parameters, this is more to give a comparison of trends rather than absolute values. So for this initial stability, these vertical red lines are an issue with the simulation, and the growth rate is in fact 0 for the entire time. And you can see that for the 20 Maxwellian, you do capture some of these positive trend of the growth rate towards the end of the simulation. Similarly, for that case of marginal stability, the 2 Maxwellian representation says there should be no growth at all. The 20 Maxwellian representation captures some aspects of this positive growth rate. And for the 1.35, the most unstable distribution, we do have the 2 Maxwellian really overestimates how much energy should be going into the plasma. The 20 Maxwellian does all right for a little while, but there is a point where the 20 Maxwellian description just completely breaks down. And so this is the linear description, the fastest growing mode for that 20 Maxwellian representation. So let's dig into a little bit about what's going on actually in the distribution functions that might cause this. So here I have, again, that dark blue, so that should be stable distribution. And I have the actual dispersion relations for a couple times throughout the simulation. So 0 is the initial time. We've got about 10 omega PE, 25 omega PE, which is the end of where the 1.75 agreed, and then also that 50 omega PE, which is definitely in the nonlinear portion for the 1.75, a little bit less so for this marginally stable distribution. So the top row is for the 2 Maxwellian fit at these different times, and the bottom row is for the 20 Maxwellian representation at the same times. So we can see that for the marginally stable distribution, they start off with a very similar dispersion relation. So there are no positive growth rates, so there's no unstable modes. But as time goes on, some of these stable modes change their position in the 20 Maxwellian representation, and they start moving up towards a positive growth rate. And so we do, by the end of the simulation in this 50 omega PE, end up with some positive growth rates, and so some actual unstable modes, which could possibly account for this positive behavior that we're seeing. This is, however, not present in the 2 Maxwellian representation, which is why that we see a 0 growth rate throughout. So for the marginal stability, we see something similar. Here I'd like to point out that in the 2 Maxwellian representation, the 2 fastest growing modes are of equal magnitude. So even for the 2 Maxwellian representation, there's no fastest growing mode that you can say all the energy should be in this single mode in order to really represent what's going on. Even in the 2 Maxwellian representation, you'd need to take into account these 2 modes that are of the same order and really are indistinguishable on this scale. But again, for the 20 Maxwellian, you can see these modes that are originally totally stable, moving across the line of stability and becoming relevant, and even on the order of these 2 most unstable modes. And so finally, for the one with a higher drift velocity, we do have the kind of a constant structure similar to what we'd expect for an unstable plasma. We have a most unstable mode, second most unstable mode stays relatively constant throughout the entire time. For the 20 Maxwellian representation, we do start off with a most unstable mode and a second most unstable mode, but throughout the plasma, again, we have these other modes that were originally unstable, moving up, crossing the line of stability, originally stable and crossing the line of stability and becoming unstable, kind of when we see these strong changes in our ability to reproduce actually what's happening in the plasma. So there's a point at which the linear description breaks down and we can no longer predict what is happening for the fastest growing mode. So I'd like to point out that this estimate of the power in the fastest growing mode isn't just a function of gamma, it's also a function of k. So it's not just what is the power in the fastest growing mode, but it's the power in the fastest growing mode for each length scale. So to truly describe what is happening in the plasma, it's possible that we're going to need to include not just the fastest growing mode, but also the ones that are of similar order, both in frequency and space. And so in order to do that, though, we'll need to figure out how much energy is in each particular wave, this E naught for each fastest growing mode. And so in order to do that, we'll need to add in some sort of wavelet. We need to add in some machinery to our linear description of the plasma. And so that's going to be very important for actually getting out a better linear description of the plasma in the mode. And so that's something that I am working on for the moment. So just to sum up, so we're representing the representing the distribution function using n Maxwellians and capturing all the information in the linear description of the plasma is going to better allows us to get a lot more information out to better represent the actual behavior of the plasma. And so even small deviations in the phase space can make a big difference in the predicted growth rates. And in order to properly capture the behavior of marginally unstable plasmas, it may be necessary to include power in all the modes present, not just the most unstable mode. So with the effects of spatial variation, there may be stronger limitations on the use of linear theory than previously thought, but that's not a topic that it's beyond the scope of this present talk. So thank you for your attention. Are there any questions?
Great, Emily. I know I have a question, but anyway, but let Nick have a question about if the negative values in the plot were decays.
So
yeah, hey,
yes.
sorry, that was a clarifying question. I was trying to wrap my brain around your color plots, the mode plots, and I think I finally managed it at the end. But
yes.
I think so my more general question is so how am I supposed to interpret 20 Maxwellians?
So
Oh, did I miss something at the beginning? I'm sorry.
Oh no.
So is it really 20 different populations of plasma that I'm looking at, or am I?
I would interpret them as so instead of, I think of it as, so usually when we represent a distribution, we say, okay, we've got V parallel, V perp. And so I've got 512 points and they each have a V parallel and V perp. But instead of describing it by its velocity coordinates, I'm describing it by these, I'm basically changing the basis. So I could change to like E and theta, but here I'm saying, I'm representing it as kind of the sum of Maxwellians, the same way like I could represent a delta function as a sum of Maxwellians. You just need a lot of them. And so it's less, we're using Maxwellians less as a saying it represents kind of like a population of plasma, and more it's just like a coordinate.
Okay, thank you.
Yeah.
Sorry, I muted myself. Anybody else has a question?
Yeah.
Excuse me. Martin had a question. Hi, Lama.
Yeah, on the subject of the Maxwellian decomposition, I just add that it's a very common thing if you do what I do, and you use non-Maxwellian distributions to calculate the ionization balance or the emission spectrum from such a plasma.
Yeah.
You have atomic rates tabulated as a cross sections integrated over Maxwellians.
Mm-hmm.
If you represent the distribution function by a sum of Maxwellians, then it's an easy time to reconstitute the collision rate, or with the non-Maxwellian distribution function if it's set up as a sum of different Maxwellians. This makes our life easier.
Yeah.
I know it's some distance from what you're actually doing, but it's I think in general a good thing to try and do if you can.
Yeah, absolutely. And frankly, something that I've been thinking about is that given the limitations of spacecraft data specifically, Maxwellians may not be the best. If you have limited points of velocity space and you need 10 Maxwellians represented, maybe you could use a kappa and use 6 and get a lot more bang for your buck. But that requires a reworking of the.
But the kappa distribution has to be decomposed into Maxwellians for my purposes.
Yeah, that's exactly the same problem. In order to use a kappa distribution, I'd need to totally rework all the mechanics of this linear calculation,
yes.
and it's a lot of math.
But there is some machinery available for kappa distributions. I mean, there are redistribution functions for radiation transfer and things like this. But
yeah, but it is so much preferable to this is exactly why I'm doing this. Using the existing machinery for Maxwellians is just very much preferable situation.
Yes, yes, of course.
Question, Emily, in terms
Yeah.
of, did you compare this with simulations?
Yes.
This approach.
Yes. So it's just,
sorry, I missed that part. Okay.
oh yeah, sorry. I kind of sped through it. So it is a fully consistent 1D, 1V electrostatic solver. So the actual distribution that I'm representing in Maxwellians, it's a full distribution when I put it through the simulations. It's just that after the simulation is run, I say, how close of fidelity can I represent this distribution? But yeah.
Okay, great.
Yeah.
I missed that. Anybody else have any other question? We might end up short,
Yeah.
finishing earlier than
Yeah.
in general. Great. Emily, do you have any advice for younger generations coming in, since this is a young voice webinar? For community, one of the issues that we're dealing in our outreach is how to build community and how not to feel alone, how to find mentors. So if you have any advice or topics you're interested in, you can mention here.
Yeah. So I feel like I've really benefited from also just groups of peers. So these are people in my PhD program, people I've made friends with at conferences throughout the way. And so I've really been leaning on them through the pandemic. And so
especially in the pandemic, you're
yeah,
right.
very much so. But even throughout grad school. And so I would say just reach out, because everyone's probably in the same boat that you are.
Right. And I found also extremely helpful being proactive in finding mentors, charting your way. That sometimes you don't even have, prior examples to look to the left and right that were like you. So you really need to reach out.
Yeah, very much so.
Sounds fantastic. And I know you're running a very successful group yourself for a Plasma seminar. So I think it's another way of creating a group and a community.
Yes. Yeah, I've really benefited from, so I have put together a kind of a physics discussion group.
Right, and I think this is a phenomenal idea. Yeah.
Thank you. Yeah.
Thank you so much, Emily, for taking time. I hope you guys come next month. We're going to have a break in August, but next month, yes, thank you. We are going to have a break in August, and next month we're coming back to not science, but to talk about trajectory again. And then this is a Latinx experience. I'm looking forward to hearing that. That would be really interesting. So join us at 3 o'clock with Nick running the happy hour. Nick, you want to put again in the chat, you can see the social happy hour link, it's up there. I also put a link for the survey. If you want to put ideas for webinars, we will have other, we are booked until December, but then we have open slots so we can start filling out new ideas for new webinars. And we are open to suggestions, both in science and both in just outreach in general. Thank you so much, folks. Okay.
Thanks for having me.
Bye, folks.